is actually, it looks bluer because when you look at stars, the hottest stars are bluer, and then the cooler stars are redder, more red. Okay. Okay. So recording is started. Audio is good. So now we can move on and talk about the solution of the homework assignment. So I'm going to leave this one up. Okay, this is a slide of the Tower of Hanoi problem, and it is recursive. Okay, it has subroutines. So we can potentially look into this, as one of the things that we can do, as an example for this class. Does anyone? Yeah, go ahead. You don't like that. The Tower of Hanoi is a problem. So according to legend, okay, there are some monks, with up in a, okay, I cannot remember. They talk about it. It's like Brahma, temple or something like that. And the idea is, there are 3 poles with 64 golden discs on one pole, okay. And the rule is you can only move 1 disc at a time. And the idea is to move all the discs from the first pole using the second pole to the third pole, okay? But there's one additional rule, because if the only rule is you can only move 1 disc at a time, then 64 moves will finish the task, right? You move the disc one by one to the middle one, and then you move everything from the middle pole to the last pole, you're done. So the second rule is you cannot put a larger disc on top of a smaller disc. So that turned out to be the killer, because now you have to think of a way to make sure that you do not place a larger disc on top of a smaller one. So it has to stack like this, okay, like a pyramid. So as it turns out, the problem has a complexity of 2 to the power of the number of discs. So since we have 64 discs, it will take 2 to the power of 64, the whole thing minus 1 many moves, in order to finish the whole thing. So the idea was when someone can complete this task, it will be the end of the world. That was kind of the legend, okay? So they have 64 discs. If you can play by these rules and move all 64 discs from the first to the last pole, then that signifies the end of the world. So I went through some simulation, and go like, okay, let's estimate it would take only 2 seconds to move 1 disc from one pole to another pole, okay? So 2 seconds times 2 to the power of 64, the whole thing minus 1, turns out to be 1,000-something billion years. And the sun is going to go, not supernova, it will just kind of expand to become a red giant, but the sun's photosphere will actually be beyond the Earth's orbit at this time. So we'll be all inside the sun within about 4 billions of years. So I'm not too concerned about 1,000-something billions of years later. Okay, 4 billion years is kind of one of the crucial points. If we're not ready to migrate, to outer space, we'll be all living inside the sun for a short amount of time. Yes. So anyway, that was the story behind the Tower of Hanoi. So next time you do a homework assignment, with Tower of Hanoi, you kind of know the background of that little story a little bit, okay? Which I think is kind of interesting.
So when they created it, did they know about the time complexity of the Tower of Hanoi?
I do not think so. They just knew that it was a difficult problem to solve, and then they say, okay, by the time we can get this problem solved, it's going to be the end of the world. So as it turns out, that's so far in the future that it doesn't really matter. All right, so we'll deal with Fibonacci first, okay? And in the process of answering the question of Fibonacci, I think that's actually a good review of the material. And you can probably expect your final exam to involve the same kind of reasoning, the same kind of material. So that's why, this is actually a pretty good thing to go over, in the context of reviewing for the final exam. I think I've talked about, when the final exam is. Yep, okay. All right, so here is the Fibonacci code. I'm going to copy and paste it into an editor just so that it's easier to read. So let me see. Yeah, I got one here. Oh, okay. I talked about it yesterday with the other class, so it's still here. And then the code is, this is not it. This is from my cisp310 class. I'm going to save this. And what was yesterday's date? 10. Okay. All right, so I can get rid of that. And I don't have a new one. That's fine. We'll open a new window. So we'll go ahead and take a look at how to write this program. If you got it done, by yourself, and you turn it in, that's all good, okay? But I'm still going to talk about it a little bit because your method may not be entirely the same as mine. So we'll go ahead and talk about it. All right, so this is a subroutine. The entry point is called F. So if we have a single label F to mark the entry point of the subroutine, and it has only got one single parameter. So if we want to do it, the usual way, using labels, I can still do it the same way. So n is going to be return address 1 plus, because it's 1 byte on top of the return address. Now in the test, in the final exam, you are not required to use labels. So if you choose and go like, well, labels is a feature that was added later to the assembler, I don't feel comfortable using it, you don't have to use it, but you're expected to understand it. So if I give you code that involves the use of definitions of labels, you should understand what those label definitions mean, okay? All right, so now we go in and we have no local variables. So there's no decrement D, inside the subroutine to allocate for local variables. So the first thing we need to do, this is a ternary expression. So the first thing we need to do is to evaluate the first part of the ternary expression. So we need to find out whether n is less than 2 or not. So the first thing we need to do then is to load some register with n, and then add AD. So the register A is now the address of parameter n, but we don't want to have the address of parameter n. We want the actual parameter n. So that means we have to dereference that. So now A is actually parameter n. And then we'll use another LDI instruction and load the constant of 2 into another register. We'll just put it into register B. And now we have to compare those two. So depending on how you want to do this, some people like to stick with the ordering of the same original comparison. That's cool. Some people like to optimize for the least number of conditional branches and unconditional branches. That's fine too. So whatever way you do it, you just have to make sure that it follows the logic of the C code. So if I want to do it in following exactly the same order, which is comparing n to 2, I would compare A to B because A has n and then B has 2. So now the question is, how do I do the conditional branch? You have to look at your inventory of available conditional branches. So the first thing is, we know that we need to know which one is smaller, okay? And n is unsigned, so that means which flag should I be using to tell whether a number is less than the other number or not. The carry flag, very good. The carry flag is also the borrow flag, which is set or cleared by a subtraction, which a compare really is. Is that okay? So we need to use a JCI somewhere, okay? So now the question is, what does it mean when A is less than B? That means n is less than 2, but that means we also need to go to the then branch, okay? Or go to this the second expression. So this is going to go to the then branch or then expression. EXPR for expression. But what does it mean when the borrow flag or the carry flag is cleared? That means n is at least 2, in which case we have to go to the else expression. So if you want to use the same ordering in the comparison, this is pretty much the only thing you can do. Now you can also do the opposite. Instead of comparing A to B or having A minus B, you can also flip the order and have CMP BA, in which case you are now subtracting n from 2. So the way you do the branching will be different, but it is possible as well. Okay, so I'm only using one particular way, and we'll just stick with this method here. So that means you need to have then expression as a label and an else expression as a label as well. The then expression will definitely need an unconditional branch to branch around the entire thing to go to the end of the ternary operator. So I'm just going to call this end turn, or end of ternary operator. And then the end of the ternary operator is going to be here. In other words, if you look at this, this is really the same kind of control structure like an if-then-else conditional statement. That's because a ternary expression really is a conditional statement, except it deals with values instead of statements. That's the only difference. But in terms of, there's a condition to evaluate, there's a then branch if and only if the condition is true, and there's an else branch if and only if the condition is false. That part is identical to a if-then-else statement. Are we okay so far with that concept? All right, cool. All right, so now we have to figure out, okay, what should we do, or what should we return when we are dealing when n is in fact less than 2. So we are talking about just this n here. Oh, we got n in the register already, don't we? In fact, we have it in the right register already, which is register A. Okay, we got nothing to do. Okay, so I'll just comment here just so that we know why there's nothing here. Okay, so I'll just say nothing to do. N is in register A already. Okay, done. So the else expression is the one that is complicated because we have to call Fibonacci again twice. The first time we have to call it with n minus 1 as an argument, and then the second time we have to call it with n minus 2 as an argument. So now we'll deal with the first one first. Okay, since A already has register n, we'll call it with that. So the first thing I'll do is to decrement A, because A is already n. So in this case, A becomes n minus 1 because of the decrement. We decrement D, we push it on the stack, which means we are doing STDA. So we are pushing n minus 1 on the stack. Then we have to push the return address, which is a LDI A, and then using the postfix notation, .6+ is the way to do it. If you insist and go like, I don't like to use a postfix notation, I would much rather stick with a label, you can do that as well. It's just that you have to remember to define the label at the correct place to mark the return address of this particular call. So you can do either way, okay? As long as I see that you understand how to call a subroutine, it's fine, okay? So you have a lot of alternatives in terms of how to implement the program, how to specify the code. And then we have a decrement D, and then the STDA, and then we have a JMPI to the subroutine, which turns out to be the same subroutine that I'm in right now, which is F. Upon returning, I got one thing to do because I have to deallocate the argument that is currently on the stack. So an increment D would do that. But at the same time, because I know there's a second call to Fibonacci, which will overwrite register A, because register A, after all, specifies the return value of a subroutine call, right? So right now I have register A being the return value of f of n minus 1. But if I don't do anything with A right now and I call f of n minus 2, then register A will be updated to become the return value of f of n minus 2, and I would have lost the return value of f of n minus 1. So I need some place to put my current return value. Another register is not a good idea, okay? Because when you call a subroutine, that subroutine, whatever you're calling, can destroy registers A, B, and C. So you don't want to put it into just another register. The safest place to put it is on the stack, okay? So that's why I need to push the current return value on the stack first, which means I'm going to have a decrement D again. This time I'm going to store A onto the stack. So this is basically pushing the return value of f of n minus 1 on the stack. So nobody can touch that. Then I'm going to push n minus 2 on the stack and then call Fibonacci again. So I need to go back to n But this time, if I go back to n, I can use about the same thing, which is load A, but this time it has to be 1 plus whatever the label n is defined to be, because I have one extra thing on the stack right now, which is the return value of f of n minus 1. So I have to remember to add this 1 byte here, and then the rest is about the same, okay? And then we will push that, we'll decrement it twice. Oh, we have to load it first, because at this point A is the address of parameter n, so we have to do it indirect here so that A becomes the actual parameter n. Then we decrement it twice, so it becomes n minus 2, and then we push it on the stack. So decrement D, store that to whatever D points to. So now we have n minus 2 pushed on stack. Then we can do the usual call, which is LDIA and then dot 6 plus decrement D, STDA, JMPI to the subroutine, which is F. And when it returns, I have to deallocate the argument. So right now, at this point, what is the stack pointer pointing to? N minus, no, n minus 2 is just deallocated by the increment instruction. Let me move that, sorry about that. So n minus 2 as an argument is just deallocated. What is right below, what is right above that? What did I push before the argument, n minus 2? What was in A, which is the return value of f of n minus 1, okay? So I'll write a comment here and say, D points to the saved value of f of n minus 1. But at the same time, we also have A being f of n minus 2, because we just got back from f of n minus 2, and register A is supposed to be the return value of f of n minus 2. I need to add these two things together, okay? It would be nice, okay, if I can do something like this, okay? If I could, this is kind of what I want to do. Whatever the stack point is pointing to, I want to add that to register A, but I can't do that, okay? This is not supported by the processor architecture. So I can't do this, which means I have to pop whatever the stack point is pointing to into another register first. So I have to do a load instruction and then increment the stack pointer. So this way I am popping f of n minus 1 from the stack to register B. So it is now in register B. Once it's in register B, it's pretty easy to deal with. I just add B to A, and now the result is done, and the stack is balanced. So when I get to end ternary, I can now just do the usual return thing, because register A has the correct return value from both branches of the ternary operator. So we do LD B D, increment D, and then JMP B. There we go. So are we okay with this code, or do you guys have any questions about it? Yep.
I just want to clarify that.
Uh-huh.
Anytime we're decrementing or incrementing D, we're only changing our position on the stack.
Correct.
And then anytime we're incrementing or decrementing an actual register, we're changing the actual value that's in the register.
Well, okay. So I'm thinking about why you asked the question. So to answer the question itself, register D is no different from any other register. I could have designated register C as the stack pointer if I chose to. So incrementing and decrementing D is doing the same thing as incrementing and decrementing any other register. You're changing the value of the register itself. It is not affecting any memory location at all. Okay, so increment, decrement only affects the register. Now, register D turns out to be special because we agree that that would be our stack pointer. So the role of register D is special, but it is, as a register, it behaves the same as any other register. We just give it a special role that it has to perform. Is that okay? I mean, does that answer the question, or does it address the motivation behind the question?
Well, you confirmed what I know.
Okay. So that works. Yep.
So register D, it pretty much holds sort of like a label for the RAM location, right?
It's kind of like a bookmark, okay? So imagine it's a bookmark on your notebook, okay? So before the bookmark, those are the pages that are in use, and then after the bookmark are pages that are available, they're not in use. Is that okay? So when you're pushing, what you're doing is you're moving the bookmark to the next page, so that you're reserving, now you have one more page that is in use, okay? And if you if you move a bookmark back to an earlier page, you're deallocating that page. Basically, this page is no longer in use. What about the content of that page? If a page is no longer in use, then somebody could borrow it. Somebody can come in, while you're not around and go like, oh, I see, what's your name? Search. So they can say, oh, I see the search is using all the pages before this bookmark. I'll just, jot down some notes, after the bookmark. So they can potentially overwrite anything, that is after the bookmark, but they will respect the bookmark and say, I'm not going to change anything before the bookmark. So you better not move the bookmark unless you know for sure that you don't need the page anymore. Is that making any sense? So before you want to use a new page, move the bookmark first. Because if you start to jot down something on a page that is after the bookmark, and then decide I need to go to the bathroom, and then the next student comes in and go like, oh, I see search is not using that page, they can overwrite what you just wrote. Because according to the rule, anything after the bookmark is fair game. But anything before the bookmark, they cannot touch. So it's the same thing with a stack pointer, which is basically just a bookmark. Is that okay? Is that analogy working or making it more confusing? Okay, go ahead.
Maybe you could explain one more time why you couldn't add the deallocated D register to A. You said I might have done something like that.
I don't understand what that means.
There was something that you told us it will not work in the assembler. I think
Oh, the add instruction?
Adding A to the
Adding a, okay.
reference D to A.
Yeah, okay, so I will address that. You had a question as well?
I understand the code, the C code,
Mm-hmm.
Fibonacci is n is less than 2, then return n, right?
Yes.
Okay, so could you go back up to the
Okay.
so to do a return, right?
There's no return. It jumps to the end to do the return. So you can see how it is going to the label. So I don't like to do a return sequence in the middle of a code. So I just jump to the end turn label, which is all the way down here, to actually perform the. Okay, so when we talk about return, we have to clarify. Are we talking about returning a value to specify the return value, as opposed to actually going back to the caller? Yeah, so we only have one single point to go back to the caller. The other one just performs an unconditional branch to this label to go back to the caller.
So what if we did that inside of the third?
It will still be fine. Yeah, so that your code will still be doing what needs to be done. It's just personally, I do not like to sprinkle this sequence of code, all over the code. So to get back to your question, okay? So the other question was, why? Okay, I'm just going to put it down here. So the other question is, why can't we do this? Which, according to the syntax, means it will take whatever D is pointing to, in memory, and then we'll add that value to register A. The reason why this cannot be done is because we don't have an opcode to do this. Not only that, what this requires is we need to have a path from the data bus of RAM going into one of the two inputs of the ALU, which we don't have. Okay, there's no such path in the processor architecture itself. So even though syntactically it seems to be okay, because this is how we use the LD instruction, right? But it cannot be done because the architecture does not even support a pathway like that. Now, even if the architecture supports a pathway like that, we still need the opcode itself to be assigned, and we need to have the microcode corresponding to the opcode to be implemented in order to do something like this. And all of those things are missing in the architecture. So that's why even though on paper it seems like, yeah, we should be able to do this, in reality we cannot. And the same thing applies to adding a constant to a register. In other words, you turn this into a 6, okay? It still doesn't work because there's no way. Once again, this also relies on a path from the data bus of RAM, which is where a byte will be representing the 6 in memory. We need that path from RAM, from the data bus of RAM, to directly connect to one of the inputs of the ALU in order to support this instruction. And that is entirely missing. We can't do that. Is that okay? So, yeah, go ahead.
I have another question.
Yeah, go ahead.
Can you talk about line 32?
Line 32. Uh-huh.
LDIA and then dot 6 plus.
Uh-huh.
I know dot represent the current address.
The current address, the address of the LDI instruction.
Okay.
Uh-huh.
So 6 bytes after.
Yes.
Will be the JMPIF.
No, it will be the byte after the JMPI instruction.
So increment. D.
Yes.
And then so basically LDIA comma D or not.
No.
So what actually happened?
Okay, so dot 6 plus means, we are looking at the address of the LDI and then add 6 to it, right?
Yes.
So LDI itself takes up 2 bytes. So we got 1, 2, 0, 1. Decrement takes up 1 byte, 2. ST instruction takes up another byte. So we got 0, 1, 2, 3. And this is 4, 5 because it takes 2 bytes. So 6 is going to be, so dot plus 6 is the address of the increment D instruction. So we are loading the address of the increment D instruction into register A, and then we push it on the stack. That's our return address.
I don't understand how, so we just take the address of the increment D.
It is the same thing as taking the address of the increment D opcode, correct. But instead of using a label, I'm calculating it based on the address of the LDI instruction. Is that okay?
I think I will ask you later.
Okay, go ahead.
Would it be better to understand it if we just add like a space on the JMPIF and then just comment this is the return address, or like a line, so like that it jumps
Okay.
right before the D.
I
That's how I understand it.
I think his question was actually a little bit more than that. Okay, so basically we say, the following is where we should return to, and that's why the address of that increment instruction on line 37 now is loaded into register A and then got pushed on the stack. That was go ahead.
Oh, I was going to say, could you use a label to do the same operation?
Yeah, you can use a label.
Yeah.
But I want to avoid the use of labels, because if I use a label, then I can use the wrong label and then it will just branch to some other place. That makes a really good question, by the way, is to give you a program that doesn't work, and one of the problems is I used the wrong label, to push on the stack, and so the return address is now at the wrong place. But that's the reason. If I use .6 plus, I'm not relying on the label. I cannot be. I mean, if I do the calculation wrong, like, if I put a 7 here, then obviously we'll get to the wrong place. But the idea is these 4 instructions, lines 32 all the way to line 35, these 4 lines, it's kind of like a template, okay? If you want to call, plop that in, and then just change the JMPI instruction to go to a different place. Okay, that's the idea. It makes it very mechanical, as opposed to, I need to define the label and make sure that I use exactly that label in the LDI instruction. I think this is it has less chance of having errors. But that's my preference. It doesn't have to be your preference. Yep.
Another thing is like if you didn't use that postfix notation,
Uh-huh.
you'd be decrementing A 6 times, right?
Why would that be?
Or I'm sorry, you'd be actually using the opcode decrement a bunch of times.
No.
Space, right?
No.
For
Okay, if you just say LDI dot 6 plus, then you are using the unary addition, which the assembler does understand. So your plus 6 is just 6. So it would be loading 6 into register A, which means the return address is at location 6 in RAM. Yeah, which is probably not where you want to go. Yeah. Is that okay? Okay, cool. All right, so this is what I claim. I claim this program does work. So what do? We have to test it, right? Okay, so let's see how we can test this program using the minimal amount of code. So to use the minimal amount of code, I just do a LDI D0 to initialize the stack pointer. And then I'll do a LDI, register A is fine, with whatever I want to use to pass to it. Okay, when I test this code, I would test it with f of 0 and f of 1 first, because those are the non-recursive cases. So I will push this on the stack, decrement D, stda, and then I'll do the call, LDI a dot 6 plus, decrement D again, stda, and then jmpi to f. When it does return, I'm going to increment D to balance the stack, because there's an argument on the stack, and then I'll halt. In other words, I'm just calling the subroutine without storing the return value anywhere. I don't really have to, okay, because I'm putting it into register A, and I can just inspect register A by the time I get to the halt instruction to see if it has the right value. Is that okay? Is that working okay so far? Okay. All right, so we're going to give it a try. So go to the browser and see if I have an assembler already up and running. And I think I do. Yep. It already has this, or something very close to this program from the Monday Wednesday class. I was joking with my Monday Wednesday class and go like, well, the easiest way to teach the Tuesday Thursday class is to replay the video captured on Monday. There we go. So we got this code in, and I think there are no errors. Oh, there are errors. Okay, where is my error? Oh, okay, because I intentionally put this instruction here to explain why it doesn't work, so obviously it is an error. If it's not an error, then I'm in big trouble. All right, so that's good. We save, download as CSV, and we'll call this fib.csv. Replace the one from yesterday, and I don't have I should have that. Okay, we'll restart it. Okay. There we go. So now we can just run the code. Control K. We get to the halt instruction. And the only way to tell whether the program worked or not is to look at the register bank. So register A is 0. That's good, because f of 0 is supposed to be 0. And the stack is balanced, so D is 0. So that's good. Okay, we got pretty good signs that the program does work. So now we have to test it with different values. So to test it with different values, you might think, well, then we have to go back to the assembler, change that line, download the file again, put it back into RAM, and then do the whole thing again. Well, you could do that. That would work. But we also know that this byte here, the byte at location 03, is the byte that we need to change. That is the very same byte that we are pushing on the stack. So we can just change that byte if you want to retest the program. But to reuse the same instance of the processor without resetting the entire thing, because if you reset the entire thing by Control R, the content of RAM will also disappear. So we can't do that. So the first thing we need to do is to make sure the clock is at a low state. Okay, so make sure it's a dark green here. Then you can just click the reset button here. This reset button only resets the processor. It does not reset RAM. So that's the cool part of it. You can keep all the content in RAM by pressing that reset button. And then we go to the location that we want to hack, which is this location here, and we change it to a 0, 1 because we want to try f of 1, which is the second non-recursive case of Fibonacci. So now we can Control K again. The whole thing stops. We look at the register A in the register bank, and it is 1. F of 1 is 1. That's good. Register D is not is also 0, which means the stack is balanced. So this is all good. So now we can try it with different values. But once again, one thing you have to keep in mind is the clock has to be at a low state when you reset the processor. Okay, so that's kind of important. Okay, come on, reset. Say that one more time. No, you can reset first and then change the byte because execution has not started yet. I'm just resetting everything back to the original state. So now we can change this byte here to something else. I think f of 5 is 5 itself, so let's try f of 6. So we are changing that to 0, 6, Control K to start clocking, and this will take a little bit longer, not that much. And then we look into register D and see what the register A, it has a value of 8. So we want to now find out whether f of 6 is 8 or not. And of course I cannot remember, so now we can just look it up. Fibonacci, and then we just have to count because we're looking at f of 6. So we got 0, 1, 2, 3, 4, 5, 6. So f of 6 is in fact 8. So the program does also do it correctly recursively. Are there any questions about the program and also how I tested it? Yep.
So in RAM, you knew that the byte we were supposed to be looking at was the third byte.
Yeah.
In our program, that's where we actually give, I think it's register A.
Yep.
Value.
And that, I know it because I've done it before yesterday. But if it's the first time you do it, you can go to the assembler, go to the assemble tab, because the assemble tab shows you, what bytes is where according to which mnemonic. So it is this 0 that we want to change, right? So it would be corresponding to this particular 0. But that particular 0 has an address of 03 because the 6C, the actual opcode, has the address of 02. So the next byte has the address of 03. So that's how I can confirm that it is the byte at location 03 that controls the value of the argument that I passed to Fibonacci. Is that okay? It's a shortcut, it's a hack, because the correct procedure is to change the source code, reassemble, download the file, and run it. But I decided to kind of shortcut the whole process by doing this. I didn't want to introduce it because it does require you to be careful. In other words, your clock has to be at a low state, and then you click the reset button. That part is very important. If the clock is high and you press the reset button and you change it, it's not going to work correctly because the microcode engine is off phase, so to speak, compared to what it is supposed to be. Yep. All right. Any additional questions about this program? I think this program answers a few questions, regarding how to call subroutines. The most important part, the killer part of this program is, let me go back to the source code. And so in the C code looks really clean. You call F once, and then you call F again, and you add the return values. But the biggest problem is when you call F the second time, it's going to overwrite potentially all of the registers. So the original return value of F of n minus 1 will be lost unless you save it somewhere safe. And that is the reason why I gave you guys the 12 program, the 5, 7, 12 program, to illustrate, oh, okay, you can use this trick. Save the return value of the first call on the stack first. Is that okay? All right, cool. So are we done with the Fibonacci program? Are there any additional questions about this one? Nope. Okay. Was it difficult? Was it a difficult program to write? Well, I watch your Bruce Lee movies, and he does make the nunchuck look very easy to use too. I wouldn't touch a nunchuck, okay, because I'll be hurting myself. It takes a lot of practice. I mean, I have years and years and years of practice. But what I'm trying to explain are things that you can do. I mean, even though you may not have, let me count. Like 30 years of experience, doing programming, even at the assembly level. So you may not have 30 years of programming experience under your belt, but the reasoning is something that I can explain. Okay, how to approach it, how to check it, and so on. Okay, so you may not be able to code it as quickly as I can, just because you don't have 30 years under your belt, and you have other classes that you have taken too. So I wouldn't expect you guys to be able to do it as quickly as I can. But in terms of understanding the concepts, that I do expect. Okay, so I'm trying my best to explain the concepts, and hopefully you guys understand the concepts. Is that okay or not? So that was an interesting comment. Thank you. All right. So with the I meant to ask another question to follow up. What was the difficulty? Was it? Yeah. Go ahead.
For me, it was keeping track of what was in the register D.
Uh-huh.
And what was changing in the registers I was using. So, and I wasn't sure when to actually dereference our register D, the stack pointer.
You do not dereference register D often, because register D points to the return address most of the time. So the only time you really want to dereference register D itself is when you're about to return. Okay? So most of the time you're dereferencing something else rather than the stack pointer itself. But if the question is whether to dereference or not, then the concept that you need to kind of reinforce is, what is the register containing? Is it containing the address of something that I need, or is it already containing the value of something that I need?
That was the hard part.
Okay, so what that means is, one thing that might help, okay, is to document the code. So you basically go, okay, what is register A at this point? Okay, so register A is now the offset of where param n is compared to where D points to. Okay, grammatically that may not be the best way, but that's what it's expressing. Okay, register A has a particular value, and the value of register A on line 15, right after line 15 executes, is the offset of where you can find param n compared to where register D is pointing to. Okay, which in this case is just 1. Okay, because the stack pointer points to the return address, and parameter n is 1 byte on top of that. Okay, so that is not really that useful by itself, but if I combine it with the second statement, then A is now the address of parameter n. So by adding the stack pointer to the offset from where the stack pointer points to the thing that you want, now you have the address of what you want, which in this case is parameter n. So in a more concise way, it basically is saying, n is the address. I mean, register A is the address of n, which is a clue to what you want, because we don't want to compare the address of n to 2. We want to compare the value of n to 2. So that's why we need the LD instruction here, So after the LD instruction, A becomes N. Why? Because we are actually doing this. The dereference is canceling out the address off. Is that okay? So I think the biggest confusion or the biggest hurdle to go over is in C and C++, when you need the address of something, it takes an operator to get to the address. So it seems like, oh, it takes more work to get to the address, but in assembly, you can see clearly that in order to get to the value of a particular parameter or local variable, you have to calculate the address first. So that's why there's this kind of disconnect, because in C code, getting the address is an extra step, but in assembly, it is exactly the opposite. To get to the value, you have to get to the address first. So I think that might contribute to kind of like, okay, but which one comes first? What do I have in the register? Because in our mind, when we're used to C and C++ programming, we kind of think that way. It's like, oh, okay, it's easy to get to the value of parameter n, but to get to the address, we have to add an extra operator. So in your mind, it's like, there's an extra thing that I need to do to get to the address. But that's just notation. Because in C and C++, if we have to specify, if everything is only the address and you have to dereference to get to the value, you'll be seeing dereference all over the place. Is that okay? So I think that's, so you have to adjust that understanding of address versus value in your mind in order to make this more native to you. So is that helping the rest of the class? Okay, excellent.
Yeah, because I always was track where like, oh, am I doing it?
Okay. Yeah, because from your questions, I'm thinking, why is that a question? So I'm trying to address, what in your mind is prompting you to ask the question. I'm not a mind reader, but I can reason things out. All right, cool. So we don't have enough time to finish one of the practice finals, but I think we can get through some of the more important ones. So we'll get to the practice final, which is linked to Canvas already, and it has been since yesterday, I think. So we'll go to Canvas and get to the final exam links. The final exam from last semester is not going to be too helpful. Ah, darn it, I got the wrong one here. Okay, so I'm going to borrow it from the other class. I think I have it right in the other class.
Isn't our final exam different from the other class?
Yeah, it's going to be very different. The reason is the other class did not, they did take exam 2, so their final exam is only going to be subroutines and stuff like that, which some people are complaining big time in the other class.
What did they say?
They say it's not fair. They say it's not fair, and I'm thinking, do you really want to have more material in the final exam and carry more points? I mean,
Oh, so why not the final exam carry more points?
huh?
So the final exam.
Yeah. For this class, the final exam carries 53% of your grade, and then the second exam is going from 20 to 27% of your grade.
That's not harder than honors.
Okay, so I think with the remaining time, I'm going to work on this one instead of the first one. The first one is the same thing as a homework assignment, where you are given the C code and you have to translate that into assembly code.
This file's on Canvas?
This file is not on Canvas. I'm going to have to put it on Canvas for this class. Yeah.
I think it is on
There's another one.
it is in the shared file.
It is in the share folder, correct. Yeah, this is in the share folder of the previous final exam, so you can find it there already. And this is the one from 17 fall. Okay, so if you go to the 17 fall, in the old final exam folder, in the share folder, you can find this one too. Okay. The reason why I don't want to use the one from the previous semester is that one involves structures. So unless you guys insist and go like, yeah, I like structures, please have structures in the final exam, I think this one is more appropriate. Okay.
I'm just worried about time management because
Yeah.
I have other students that they're like, they're in the second exam, they're like, they didn't finish like all of the questions.
Okay, so there are certain students who did finish.
Most students.
I think the ones who did not finish, I am not gonna, I cannot know why, but I can tell that they were not familiar with the material at the same level that I thought they should be. And I think it had to do with the understanding of the architecture itself. They spent too much time on question number 1, which was, like all about the architecture. And most people who said it was unfair, they did not do very well in the first question. So I think that was an indicator. All right, so this is the program that I do want to go over, given the remaining amount of time in this class. So this is a disassembling kind of thing, okay? We're trying to reverse the code from assembly back to C code as much as possible, okay? The other one, I don't think is going to be too much of a problem because we have done it many, many times in this class already, going from C code into assembly code. This is the reverse, okay? So with the reverse, how do we get started? I mean, there's a whole bunch of mnemonic here, there's a whole bunch of registers, and this one doesn't even make use of labels, okay? So what do we do with this? Check control structure. Okay, very good. Okay, so what you're saying is we try to identify control structures, okay? And why do you think control structures are fairly easy to spot first? It has labels, okay? It has labels, which stands out, okay? Labels stand out. So we got labels here. So we have label L0, label L1, and label L2, okay? So when you look at these labels, okay, you look at label definition L0, okay? And the next question is, how do we get to label L0? Okay, what are the jumps to go to label L0? Well, in the entire code here, you can see that line 11 is the only one that can go to label L0, okay? What about L1? Line 12 goes to L1, okay? What about L2? 23, line 23 goes to L2. They're all going to a quote-unquote future label. The label definition is after the jump itself. So now you ask yourself, what kind of control structure can you have in a normal C and C++ program? You only got 2 main types, okay? Conditional statements or loops. Now, I understand there are 2 kinds of loops, okay? I understand there are 2 kinds of loops. You have do-while loops, and you also have while-do loops, okay, or while loops. But both kinds of loops involve a branch or conditional or otherwise going back to an earlier label, which we do not see here. So we know we don't have a loop, okay? The second thing is, well, the only remaining thing is a conditional statement. But you can have 2 kinds of conditional statements. A ternary expression looks kind of like a if-then-else statement. We just saw that in the Fibonacci program. But you have one or the other here. Okay, is that okay? So now we have to identify, so where's the then portion and where's the else portion? Okay, the way you can tell is the then portion, if you have both the else and the then portion, the end of the then portion has an unconditional branch to branch around the else portion. So now we can see that from L0 to JMPI L2 on line 23, that's my then branch. And then line 25 is my else branch. Is that okay? So that makes the compare on line 10 to be at least a part of the condition that will tell me whether I should go to the then branch or the else branch. Is that okay? So knowing that we are dealing with either a ternary expression or a conditional statement means that now we can start to work on this. So I'm just looking at the time and try to find out, what is the best way to work on this. And let me see, do I have a journal here? Nope. Okay.
Can you also go to like examine lab or anything?
Yeah, I can continue this in the lab. But what I want to do is I want to open the PDF in Journal. So this way I can mark it up. Because I want to show you, what you can do in a test to do this. Yeah, we are also going to a lab where the one of the projector connection doesn't work. So, I mean, we can do it. It's just we'll try to do as much as we can here first. Okay, so now that we have this, okay. I need to have a better setup next semester, like something on the back to rest the screen on so I can write on it. Okay, so what we know is this part here is the then branch. And this part here is the else branch. Okay? So now the question is, how do we decide where to go? Well, if you look at this, these two branches are the ones that dictate, do we go to the then branch or do we go to the else branch, right? But what are they relying on? They rely on the L flag, okay? Pretty much the L flag is the only thing that I use to determine whether I should go to L0 or L1. Who is going to set or clear the L flag? What is the instruction that is changing the L flag right before the JLI? The compare instruction, right? What are we comparing? So I'm actually analyzing the program backwards, okay? Because I first identify, this is an if then else, but what is the condition of the if then else? Well, go back to the jumps for the labels going to the branches, right? So I'm comparing A to B, but what is A? A is loaded, the last time I changed A is on line 6. So now we want to find out, okay, so what did I put into register A for the compare? So if we annotate this, then we can see that in this case, C is the address of the return address, because the stack pointer always points to the return address at the entry point of a subroutine. That is guaranteed because that is the agreement between the caller and the subroutine. Is that okay? Then we decrement the stack pointer. Okay, that's fine, because now we're trying to track register C. Then we increment C. So what does that tell you about C? It's the address of the return address plus 1. So something was on top of the return address that is of interest to the subroutine. What can that possibly be? Huh? It's a parameter. Very good. So C is now the address of the first parameter. We know there's a first parameter. Is that okay? Then the next instruction is let me point out here. So the next instruction, LDAC on line 5, is dereferencing C. But I'm not dereferencing and putting it back into C. So register A now has what? Parameter 1. Okay, so register A is in fact parameter 1. And then what do I do on line 6? I dereference again. So what is register A at this point after line 6? What param 1 points to? Okay. So we know that parameter 1 is a pointer. Is that okay? So on the side here, as you reconstruct the C code, we know that we have a certain param 1 for sure. And we know param 1 is a pointer. What does it point to? We don't know just yet, but we'll know pretty soon. Okay. And then what do we do with C on the next line? We increment it again. And then we load whatever C is pointing to into register B. So what is that telling you? We have a second parameter. We have a param 2. Okay. So now we have C being the address of the second parameter, and then we have register B being the second parameter itself, and now we have B being whatever the second parameter is pointing to. Is that okay? So when you look at the C code, now, darn. So my palm touched the other thing here. Okay, so now we have a second parameter, param2, which is also a pointer. Is that okay? So from analyzing the code from line 1 to line 9, I not only understand what A is, what B is at the time of the compare, we also know the type of the parameters. Param1 is a pointer, param2 is a pointer. And now we have the compare instruction. So what am I comparing? I'm comparing what param1 is pointing to whatever param2 is pointing to. And then I use a JLI or JLI instruction to decide which way to go. I think that conclusively tell you what the type of param1 and param2 are. Signed integer, okay? Very good. Okay, so now we can backfill this as int and backfill that as int. Is that okay? It has to do with how we use the conditional branch. Now, there's one more thing that I can point out right now, because line 3 is decreasing the stack pointer, which means I'm allocating something on the stack. Did I use that location right away like a usual push operation, decrement D, and then immediately store something into where D is pointing to? Nope, I just allocated that byte and not do a single thing about it until much later. Okay, what is that telling you? We have a local variable. Okay, so I don't know what the type of the local variable is because I haven't seen how we use that, but we know for sure. Okay, I need to minimize that. But we know for sure that we have a local variable 1. We don't know what the type is. We know it's there. It's only 1 byte wide. Okay. So in the code here, we know that we are comparing param1, whatever that points to whatever param2 is pointing to, because that's what the compare is doing. The compare instruction on line 10 is comparing whatever param1 is pointing to whatever param2 is pointing to, and we are going to the then branch if and only if the L flag is set. Uh-oh. Why? Yeah, except it's the resolution is off.
So if we had used if there was a JCI, we would know it would be unsigned int.
Yes. Yep, that is correct.
Can you say one more time how can we know it is there's a local variable?
Line 3. Because line 3 decrements the stack pointer, which means I am allocating a byte on the stack, but I'm not using it right away. Okay, because a decrement D doesn't mean much, because I could be calling a subroutine and pushing an argument for the subroutine, but I'm not using it until much later. So that kind of tells you that I'm not pushing an argument on the stack. Okay. All right. So, okay. So we are branching to label L0 if and only if whatever param1 is pointing to is less than whatever param2 is pointing to. I think we got our condition in the conditional statement or ternary operator, one or the other. Okay. But one thing we know for sure is we are looking for something like this. Is that okay? And that is the condition. Okay, that's the browser. Okay, so we're putting parentheses around this, and then we say, okay, assuming this is a statement, the then branch is now, from line 13 to line 23. Seems kind of long. We'll deal with that later. What about the else branch? What is the else branch doing? The else branch is doing one little thing. It's like, we'll just put a 0 into register A. What is the importance of register A? Is the return value of the whole thing. Okay, so that means, in the else branch, okay, whatever the then branch is, we'll backfill this. But the else branch has got one thing to do. Looks like it's just returning a value of 0. Is that okay? Because right after the else branch, we have the usual sequence of instructions. Line 27 is deallocating the local variable, and then line 28 to line 30 is going back to the caller. So now the biggest question is, okay, what about the then branch? Okay, what are we putting into the then branch? Okay, so now we have to look carefully into line 14 and ask, what are we doing with this instruction? We know we are not pushing an argument on the stack. Why do we know it's not pushing an argument on the stack? To call a subroutine. Okay, go ahead. Huh? I did not decrement D, and there's no call here. Okay, we don't see the usual 4 instructions for calling. LDI, some register, decrement D, store something into D, and then the JMPI instruction to the entry point of a subroutine. It's nothing like that here. So we are not setting up, line 14 is not setting up for a call. I'm storing something into whatever register D is pointing to. Remind me again, did we do something with a stack pointer at the entry point of the subroutine? Yep, it's my local variable. What is in register A? It still has the same thing as in the compare instruction. Whatever parameter 1 is pointing to, okay? All right, so now we know, okay, so you can use the same notation here. So we know the first line is local var 1 gets whatever param 1 is pointing to. Is that okay? But this also means we know the type of param 1 now, or local variable 1 is an integer type. It's not a pointer because it's storing whatever param 1 is pointing to. Is that okay? All right, what about the next line? Okay, so line 14 is explained. What about line 15? So at line 15, with this instruction here, what is register C right after the decrement C instruction? What was it pointing to earlier? It was the address of param 2. So by decrementing, it is now back to the address C is now the address of param 1 again. And then we dereference it. So register A is once again param 1. And then we are storing register B to whatever A is pointing to. What is that doing? What is register B again? Now, register B hasn't changed from this point, so it is whatever param 2 is pointing to. So I'm storing whatever param 2 is pointing to whatever param 1 is pointing to. Yep, that's right. So now we have whatever param 1 is pointing to, storing whatever param 2 is pointing to. So that explains lines 16 and 17. So now we proceed with line 18. We increment C again, so the C is now the address of param 2 again. And then we do a dereference, which means register B is now param 2. And then we store whatever the stack pointer is pointing to register A. The stack pointer is pointing to the local variable, so A is now the local variable itself. Is that okay? And then after that, on line 21, we are storing A, which is local var 1, into whatever B is pointing to, but register B is param 2, so line 21 is accomplishing this. We are overwriting whatever param 2 is pointing to with the content of local var 1. So now we put it into the C code here because that is complete. So whatever param 2 points to gets whatever local var 1 has. Local var 1. But we are not done yet. There's one more thing at the end on line 22. For some odd reason, I'm putting a 1 into register A. What is the significance of register A again? It specifies the return value. So that means we are returning a 1, or we specify a return value of 1 at the end of the then statement. Okay? And then we go to label L2. Label L2, once again, is just deallocating the local variable, and then it has the normal return sequence, which is not represented in C at all. Okay, so in C, all you're going to say is, oh, okay, we have the end of the subroutine here. And now we have confirmed that this is not a ternary operator, but instead it is a conditional statement. Is that okay?
I'm not even sure what you wrote, like when you put after the local variable equals 1.
You mean here?
Yeah, like what it says underneath.
Underneath this one? This one?
Yeah, that.
Oh, this is whatever param 1 is pointing to gets whatever param 2 is pointing to. Sorry? Huh? It is the swap, yep. So but it's not just a swap, it compares first. It compares to see if whatever param 1 points to is less than whatever param 2 points to. If that is the case, it swaps. And then returns a 1 if and only if a swap actually took place. Yep.
So you said if we know that it's not a ternary operator, what would we do if it was a ternary operator?
If it is a ternary operator, then you have to find out what is the value of the expression used. How is it used? So typically, if this were a okay, so the two are, sometimes you cannot resolve one or the other, then I will count both as correct. I'm switching back to a spreadsheet, a text editor here. So in this case, the swap subroutine has a return type of int or unsigned, doesn't really matter what it is. So we have sub1 and then int param 1, int param 2. And then one way to look at this is we have a local variable, I'll call it t just so it's easier to type. And what the subroutine is doing is to say if what param 1 points to is less than what param 2 is pointing to, then we go through the exchange sequence of instructions, which is t gets whatever param 1 points to, param 1 gets whatever param 2 is pointing to, and then param 2 gets whatever t is, else, and return 1 in this case, and then else return a 0, right? So this is one way to look at it. Not intending to confuse, but to point out that there's another way to look at this. You can look at this as, we have a subroutine, same prototype, so we are not changing the prototype, but we are changing the way it is expressed. It's a single return statement, but with a ternary expression this time. So the ternary expression is going to involve param 1, whatever param 1 points to is less than whatever param 2 is pointing to. This is still the condition, but then you look at the then expression. The then you can actually do this in C. You can say t equals to whatever param 1 points to, comma, param 1 gets whatever param 2 points to, comma, param 2 gets whatever t has, comma, 1. It is a comma separated expression, which is rarely used in C and C++. Nonetheless, it does exist. So the way this comma separated expression works is it will evaluate the individual expressions, okay, but it only returns the value of the last item in the comma separated list. So it actually does the same thing as a block of statements, except it is classified as an expression. And then the then expression in this case, after the colon, is just a 0. So these two subroutines are actually doing exactly the same thing, except one expresses the whole thing as a traditional conditional statement, and then the other one expresses the same thing as a single ternary expression, after the return. So there are two alternative, answers to this question. I really doubt anyone is going to give me the second version, but it does exist. Okay, so you can actually, enter this into the compiler, and it will actually compile. Yep.
Should one of the colons be a question mark?
Huh?
Should one of the colons be a question
Oh
mark?
yeah. The first one should be a question mark. Yeah. Now it will compile. How many people have learned the comma separated list expression in C and C++? No one. It's kind of obscure, but it's really cool as well, because now we can actually specify a little block of code inside where an expression or a particular value is expected. But it does make it kind of difficult to read as well. Yep. That is correct. So as far as the test is concerned, if this is the question and you give me either the first or the second form, they're both good. Yep. The second form does give you an idea of how obscure C can be. Yep.
The second one, still need to define your local variable, right?
Yep, you still have to define the local variable t, so that still has to be done right here.
Do it in that. Did you say t equals param1?
No, you cannot. Okay, so the question is, can we put it in here? You can do that in C++, but not in C. In C, the only place you can declare local variables is at the beginning of a block. So right after the open curly brace is the only place you can declare local variables. But in C++, you can do it any place you want. So that's why there's a minor difference between C and C++, but that also tells you that some people who are used to C++, when they write strict C code, sometimes they would use features that won't compile in C. Yes, comma separated expression is common to both C and C++, and I believe all languages that are derived from C can do that as well. All right. So are we good so far? All right. So when we go to the lab, I can go over some of the additional questions if there's a demand to do it. If you guys will go like, no, we are good for the day, then then I'll have.
Can you also record it?
Only if you're there.